This video is going to be about the integration of exponential functions, following directly from the previous video on differentiation of exponential functions. We have one learning target that we are going to focus on, and that is how to integrate natural exponential functions. We're going to take a look at theorem 5.12 and examples 7 through 10. Theorem 5.12 shows us the integration rules for exponential functions. Let u be a differentiable function of x. The first rule says that if we take the integral of e to the x dx, it equals e to the x plus c. And that is about as simple of an integration rule as we have. Unfortunately, the reality is that we rarely will see just e raised to the x power. So in terms of usefulness, this is kind of a rule that is rarely going to be used. Instead, the second rule, the integral of e to the u du equals e to the u plus c, is more realistic, and they look the same. But the difference is that in the second rule, u represents a function that is going to be more complex than just x. So before we go through some examples, let's just jump over to the curriculum map for Unit 7 and take a look at the Chapter 5 review portion, where you will see the rule right here, the integral of e to the x dx equals e to the x plus c, is highlighted there. But then the big thing is that it says u sub when the function is more complex than just x. And as we know from our previous studies, when we integrate, we should be asking ourselves the following three questions. Can I use a simple integration rule? Can I simplify and or rewrite so I can use a simple integration rule? And if you can't do either of the first two, then can I u sub so I can use a simple integration rule, which more often is not as the case with the natural exponential function. So when we go back to the notes, you can see here that even though the rules are very similar in nature, the u sub portion of the second rule makes it pretty multi-dimensional. So just to kind of highlight that in our notes here, this right here is u and not x, because more often than not it is the product of a u sub, and maybe product is the wrong word to use. Byproduct would probably be more appropriate. So let's look at some examples here and take our rule and put it into use. So I'm going to make this a bit bigger so that we can see our work a little easier. Alright, so our first example, the integral of e to the 3x plus 1 dx. The big mistake that a lot of students will make is they will try to integrate this and they'll say, well, if the rule says the integral of e to the u du is e to the u du, then this must just be e to the 3x plus 1 plus c. Done. If only it were that easy, but unfortunately it's not, and we're going to show that that answer is incorrect by taking the derivative of our answer. That's the nice thing about integrating, is you can always take the derivative of your answer and check. So if we take the derivative with respect to x of e to the 3x plus 1 power plus c, we're going to find out that we do not get back to what we started with. So what would this be? E to the 3x plus 1 times the derivative of 3x plus 1, which is 3. Technically plus 0, because the derivative of a constant is 0, but we're not going to put that in. And our derivative answer would be 3e to the 3x plus 1, which does not get us back to e to the 3x plus 1. So the rule is not as simple as just saying, oh, I have e raised to a function, so the answer is e raised to the function plus c. So let's erase our incorrect work here. And let's do this correctly. So just to reiterate before we go through these examples here, the vast majority of the time we are going to use a u sub because our function is more complex than just x. And what makes it kind of nice and easy once you get the hang of it is that more often than not, what e is raised to, that function that e is raised to ends up being our u. So in this case, u is 3x plus 1, which makes du 3 dx. So we've got our e raised to the u power, but we don't want 3 dx, we just want dx. So we come over here and divide by 3. Du over 3, remember, is the same as 1/3 du. So we're now ready to rewrite our integral. Our integral is going to be e to the u power, and then it's not just du, it's 1/3 du, so we put that 1/3 out front of our integral. And now we can use our simple integration rule. So this integral is going to be equal to 1/3. The integral of e to the u du is e to the u, and then plus c. But our original integral was in terms of x's, so we are going to rewrite this by resubbing back what we called u to get our final answer. 1/3 e raised to the 3x plus 1 power plus c. And if I scroll down to the scanned in answers, you can see that they actually wrote it as e to the 3x plus 1 all over 3. They multiplied the coefficient and turned it into a fraction. Same answer as what I have circled above here, just a different way of writing it. It's good practice for multiple choice, as you are expected to get to equivalent answers. Second example here is the integral of 5x times e raised to the negative x squared dx. And this was obviously more complex than the first example, but this is definitely one where you should know I got to use a u sub because I've got a product. So the first thing I'm going to do is take that 5 and I'm going to put that in front of my integral, so I don't have to worry about it until I actually start integrating. Then I have a product here, and anytime you have a product, it's kind of a dead giveaway that you're going to have to do a u sub because we don't have a reverse product rule or a reverse quotient rule or a reverse chain rule or any of that, so we do a u sub instead. And anytime you've got that e function, again, the trigger is really whatever I'm raising my e to is probably going to be my u. This is no exception, so I'm going to call u negative x squared, which makes my du negative 2x dx. Now as I look back, I now have e to the u power, but I don't want negative 2x dx, I just want x dx. So I'm going to divide by negative 2 here. So this becomes negative 1/2 du, and now I'm ready to rewrite my integral and finish the problem. So the integral is now going to be not just negative 1/2 out front, but that 5 that was out there as well makes it a negative 5/2 out front of my integral. And then e to the u power du. And when I finish this one out, I'm just going to do everything in one felt swoop here. So I've got negative 5/2, and it would normally just be e to the u power, but I got to resub back in my x, so it's e to the negative x squared power plus c. And I could check this one by taking the derivative of it, and I would get back to what I started with back here. So if we take a look back down here at the scanned in answers, negative 5 halves e to the negative x squared power plus c, they have the answer written just like I have it up here. However, this could be written a little bit differently, because with this e being raised to the negative power, we could move the e to the x squared down to the denominator and rewrite it. Number 3, e to the 1 over x all over x squared dx. Again, definitely going to have to do some u-subbing here. But before we do that, I'm going to first rewrite my integral. And I'm going to rewrite my integral so that it's a little easier to identify what my u is going to be. So e to the 1 over x power is really e raised to the x to the negative 1 power. And instead of writing divided by x squared, I'm going to write times x to the negative 2 power dx. And the reason I do that is so that it's going to be a little easier to do my u sub after I identify u. So once I see that e raised to the power, more often than not, u is going to be what e is raised to. So e to the, or x, excuse me, to the negative 1 power, which makes my du negative x to the negative 2 power dx. And I don't want negative x to the negative 2, so I have to divide by a negative 1. But now I can rewrite my integral. So my integral is e to the u power, and then it's not just du, it's negative du. So I put the negative out front. I'm now ready to integrate. I've got my negative out front. The integral of e to the u is e to the u, but I'm going to resub back in my x to the negative 1 power plus c. Done. And if we scroll down here, negative e to the 1 over x plus c power is equivalent to my answer. They just rewrote x to the negative 1 as 1 over x. Number 4 looks complicated. We've got trig functions, but we've got the product, so u sub, and e is raised to the cosine of x, so kind of the dead giveaway that u is going to be the cosine of x, which makes du negative sine of x dx. We don't want negative sine of x dx, so we divide by a negative 1. And when we rewrite our integral, e to the cosine of x becomes e to the u power, and sine of x dx becomes not just du, but negative du. And now we're ready to integrate. So the negative stays out front. The integral of e to the u du is e to the u, so I'm going to resub back in my cosine of x, and then plus c. So when I scroll back down again, gotta kind of shift this over, and the answer is negative e raised to the cosine of x plus c power. So I'm running out of time on this video. I'm going to make a second video here shortly. The 4 examples that I've done so far are all indefinite integrals, so all of them have a plus c in the answer. The 3 examples that I'm going to do in the next video are all going to be natural exponential functions, but they're going to be definite integrals, which means we're not going to have a plus c in the answer, but instead we are going to evaluate using our lower and upper limits.